Hi everyone, this is an introduction video to help get you started with Lab3. What I will be starting off with is how to use MicroCOS 2 in Visual Studio, both locally and on Move, just to help anyone that's still struggling getting the environment set up. So what you will find in the resources section down the bottom is all the content for the MicroCOS 2. So we'll find some data sheets, some reference manuals and so on. So you should be using these in order to complete Lab 3. You will also find the base files which contain the Windows port that can be used with Visual Studio. So there are some instructions here on how to set that up, but I will be doing it now. And it should work for a number of different versions. So I'll be doing it using Visual Studio 2015 on this particular computer, but I've also tried it in 2017 and 2019 and the community versions, and they all seem to work fine. You just need to make sure that you retarget the solution correctly. Okay, so what you want to do is download the zip file first. I'll put it in a new folder. Okay, and then you want to extract those files. Okay, so we'll just extract it here. And what you'll find is you don't actually need this Mac OS folder, so you can get rid of that. Within this folder, you want to be going into evalboards, Microsoft, WinXP, Visual Studio, X1 OS, and these are where all your solution files and the C files are located. Now there is a actually no, never mind that. Okay, so now what we'll do is we'll open up Visual Studio. And then what you want to do is open a project or solution. And then go to the folder that I just talked about. And select the solution file, .sln. At this point, it may prompt you with an option of retargeting the solution because the original files were, the solution was created with Windows 8.1, I think, and an older version of Visual Studio, so you will need to retarget it to what you're using currently. Okay, so it will look, this pop-up will look slightly different depending on which version you're using, but just click OK to retarget the files. Now, if it doesn't show the pop-up, then what you want to do is right-click on this solution file, and there should be an option for retargeting the project. Now, I don't have this option here because it's the 2015 version. So it might be on the project. Yeah, so in this particular version, it's here. You can retarget SDK version. In 2017 and upwards, you can either retarget the whole solution, or there will be an option similar to that also here where you can retarget the project. All right, what you will then see is that there are few folders here. These two folders at the bottom contain all the core files for the real-time kernel, so you don't necessarily want to do anything with that. In the app folder, you'll see a number of files that are required, like app.c, app.config, example, includes an OS config. Now the file that is not necessary is the remaining files. So in this case, there is this file called example8_priority_inversion.c. These are one of the many examples that have been created by Lindsay Kleeman for the ECE 3073 unit, and it will have different types of examples of real-time applications. So you can actually use those, but we won't be using this one. So what we'll do is swap it out. We'll remove it first. So you don't want to delete it, you just want to remove it from the project. And then you can right click on the folder and add an existing item. Okay, so all the example files from the 3073 unit are all preceded with the word example and some number. So you can go through each of these, read through the comments and try to run these applications, and that will teach you some of the basics of using microC OS 2 and also real-time concepts. So this stuff is all covered in the 3073 linked material, which you can find on Moodle. So if we go back to the lecture section under week 5, here, so you'll find the lecture videos here and the notes here. And usually, well, in these videos you'll find that Lindsay has gone through some of these examples in the lecture itself. So you can refer to the videos as you try and run these code files. Okay, so what we'll do is we'll select this initial example, which is a very simple example of creating tasks. So then we can open the file, and there's a description of what it does at the top here, and there are a few different versions that you can set by changing this definition, and then these are what the versions do. Okay, so in this example there are two tasks, task 1 and the start task, and they are given certain priorities at the top here. And what will happen is the start task will run first, and then you have, depending on the version, creation of a particular task. I'm not going to go into the details of this, but what we'll do is we will just now build and run this example very quickly. Okay, so then we can choose debug, start without debugging, and there should be a window open, and once the tasks are started you should see printouts. Okay, so this is what you will see running this first example with version 4. Okay, so what you can do if you want to get familiar with microC OS is you can run through each of the different examples. So if you wanted to change the example once, again, you just remove and then you add the file that you want to test out. So you might want to check the task parameter passing next. And so through the examples, the code gets a little more complicated and there are more important things. So in this particular example, you'll find that it will show you at some point here how to run a loop that creates a number of tasks based on the same template. So there is a function called task here, which is going to be used to create a number of tasks. So it will take an argument as input, and each task that gets created with that template will get a unique priority. This is all covered in the lectures from 3073. Anyway, so you should be going through that to help you out with Lab 3, and that's how you would run code in this MicroCOS emulator. Okay, so next we'll look at running it on Move. Now the files that are provided for the Lab 3, which you will find here, this is pretty much the same structure of files that you'll find in the other MicroCOS zip file that I just showed you, but there are a few additions and a few changes to some of those files. So I just put it here so that you could just start straight away at a point where your skeleton files are all set up correctly. Okay, so you can, the 3073 examples are also within this zip folder. You will also find in this zip folder a README file amongst the other code files that will describe some of the changes Lindsay made to implement the asynchronous code, which we'll cover a bit later. Okay, now I'm going to attempt opening the Lab3 files in Move, so you can access it from your my.monash page. And you will need to be using the full version of the Citrix receiver, so the local installed application, for it to work properly. I mean, it should work on the light version, but we haven't figured out a way to properly copy the files to the VM in the light version. And the method we use for doing it on the full version is a bit of a hack. Anyway, so find Visual Studio, you might need to search for it. On Move they have the 2017 version. Actually I forgot to check. Oh yeah, so it's asking me to open it in the local Citrix workspace. You might need to change your settings for that. And the first time you open it might take a long time to pop up, but just be patient. Okay, so you can just skip this step. Just click Not Now, choose your favorite theme. I'm just going to go with the default. Okay, at this point we don't have the files on the VM just yet, so this is actually running on the VM, and you can see that if you pull it out from the maximize view, you have that black border around it, and that's how you can tell that it's not a local app. Alright, so now what we should be doing is downloading the file. So we're going to open the actual Lab3 zip file this time. So we'll download that. I'll just save it here for now. And I think what I might need to do as well is extract it. Okay, so the folder that you will get from extracting this is called Software for Students. So the only method we found so far for uploading these files is to actually copy and paste. So I'm going to click on this, I'm going to press Ctrl C, and then go back to the Citrix VM and go Open Project or Solution. And then I'm going to choose a folder. So at the moment, this should be the VM path, not my local path. So I'm just going to click in this window and Control V, and that should copy across the folder and all the files. Okay, so the other methods we've tried is drag and drop. That didn't work. And then we tried uploading through the light version, and that seems to upload it to a totally different VM altogether. But this works, so let's go with this. If you do figure out a solution, please let us know, or a simpler, more formal approach. Okay, once that's finished copying, what you can do is just click refresh, and then you will see the folder there, and then you can go down into the folder that has the actual solution files. So then you select UCOS2 solution, and this is the pop-up for retargeting in this particular version. So it's going to retarget to SDK version 10 and this particular tool set. So you can either click OK here and it will do that. As I was saying earlier, the other option is to right click on the solution, retarget the solution, and it will bring up that window. So retarget it. Now this zip file should be set up for you with the solution that has the skeleton. So this is the skeleton code for Lab3, and the other folder should look pretty similar to the normal microcos zip file structure. In the example that I did with the local Visual Studio, I had this the file that we were running within the app folder. It doesn't matter too much. You can have it either out here or you can put it into here. It's fine. So what we can do quickly, so this, I will go through this code soon, but now that I've added these two empty functions since the initial upload, what you can actually do is build it and run it as is, and you should get no compilation errors and some output. Okay, so build succeeded, and then we'll start with our debugging. And you should get some kind of output, which we'll discuss later. Now for an overview of the Lab3 task. If you haven't already, please go back and watch the second lecture of this week, which gives a description of the 2019 version of this lab. I think after you watch that, then watching this would make a bit more sense. Okay, so the task for this lab is to implement both the RMS and EDF scheduling algorithms within the microcos2 real-time kernel. And then to compare the performance of the two. So this semester, because you aren't able to access FPGA hardware, or not all of you are able to access FPGA hardware, we've decided that you'll be implementing it using the Windows port of the kernel, which, as you see, runs in Visual Studio. But there are a few caveats to doing that, which we'll talk about a bit later. So the first part of this lab is just the preliminary work, which is some theoretical analysis of a particular scheduling situation with 3 periodic processes that have different execution times. Looking at the utilization and the utilization equation to see whether it's guaranteed to be scheduled, and then looking at the least common multiple of scheduling. So I believe examples of this have been covered in lectures, so you should be familiar with how to do that. There is also tables to be completed using the RMS and EDF scheduling methods for that scenario. Okay, now the actual task starts here. So the caveats that I mentioned before are that the Windows port of UCOS2 actually tends to drop timer interrupts every now and then. So therefore it's not fully reliable. And so we can't implement the lab the same way it's implemented in past years. But Lindsay Kleeman has developed a solution to this, which uses an asynchronous timer method. So what happens is the CPU is kept busy and all tasks are assumed blocked within each tick. When all users' tasks are blocked, and then the time will be able to increment. So this doesn't actually report real time, it creates a new time basis. So what I might do is I might go to a OneNote page just to try and explain this a bit better. Normally, in a real-time system, there is some kind of regular timer interrupt that is used in order to synchronize the kernel to a real unit of time. Each time the interrupt occurs, it triggers the kernel's scheduling code, and shortly after this, the highest priority task available will then be run. What this would look like on a timeline is something like this. So you would have interrupts occurring at a regular rate. Okay, that will be some fixed period of time in the lab. That's usually 1 millisecond. Okay, now Lab3 requires you to create a task that will act as a secondary scheduler in order for you to implement your RMS and EDF scheduling. This task needs to be given the highest priority so that it is always run first after the timer interrupt. So that means it would look something like this, where after every timer interrupt, the first task that is run is your secondary scheduler. Within that task, you would have code that decides, based on whatever scheduling policy you're using, which of the ready tasks is to run next. So what you might have is that, let's say, you have some process P1, which might take some amount of time to run, okay, and then it will go to sleep for 2 ticks. Then you might have another process 2, which takes a longer amount of time to run, so it doesn't complete before the next interrupt, and it will then continue after that scheduling task has run. And then finally you have some task 3, which might go for an even longer amount of time. So it gets interrupted by that third timer interrupt, then the scheduler will run, and now task 1 should be ready to go. I've actually used the same colors there. Anyway, so your task 1 will have woken up again, so it can run. And then now your task 3 will complete. Okay, and then now that all 3 tasks have finished and they're waiting for their next period, you might have some amount of idle time here before the next timer interrupt. Okay, now what you'll find in when you use microcos2 in the Windows port is that the timer interrupts sometimes get missed. So if we were to go through that same example with some timer interrupts missed. So let's say we missed that one. So on and so forth. So what it would look like is that the scheduler will still run right after each timer interrupt. But now you will have this situation here where task 3 is able to complete because there is no interrupt to stop it. And then the next time that task 1 runs, which should have been somewhere here, is now delayed to this point here. Okay, and so that's the issue that we run into when using microcos2 in the Windows port. So what Lindsay Kleeman has done to solve this is to create code that removes the synchronization of the system to real time and now makes it aligned to a number of ticks that have occurred or a number of interrupts that have occurred. Now I'm going to try and draw this out as I did for the previous ones. Okay, so now what you would have is a timeline that is relative to a number of ticks. Okay, so before you had real-time units, so you would have interrupts occurring, for example, at 0 milliseconds, 1, 2, 3, 4, 5, 6 milliseconds. And in the case of the one where it dropped, it would be 0, 1, misses 2, 3, and 4, and 5 milliseconds. So in those cases, the task had a amount of execution time that was a real time unit. So maybe we'll say that task 1 took some proportion of a millisecond, maybe 0.7 milliseconds to execute, and process 2 will say takes 1 millisecond to execute, and 3 will take maybe 1.5 milliseconds for of execution time. So in order to change to this new time frame, we need to change the execution time as well to some proportion of a number of ticks. So what that might look like is that you will get an interrupt here. You will still have your scheduler code that runs first. Then you will have your task 1, which will run for 0.7 ticks. Okay, then what's left in that tick is 0.3 ticks. So you would have 0.3 ticks worth of process 2 that would run. And now you have used up that whole tick. So what actually happens with Lindsay's code, the way he's done is there is now another task, we'll call this task X, that will run and keep the processor busy for the remainder of that particular cycle before the next interrupt. So it blocks all other tasks, and then all it does is it will increment some count that keeps track of the number of ticks that have occurred. Okay, and then at some point you will have the next interrupt occur, and that will be the start of the next tick. So now you would have the remaining 0.4 ticks. Oh, sorry, first you would have the scheduler. Oops, that wasn't right. You would have the scheduler that would run first. It would decide that there are still 0.4 ticks of task 2 to run. Then it would run 0.6 ticks worth of task 3, and then up until the next interrupt you will have that task X running to keep everything blocked, and then it would also increment the count of ticks. Okay, then there would be another interrupt here, and so let's just fill this out till we get to the point here. So then what you would have is you would have task 1, which will now run for 0.7 ticks, and then you would have, for example, task 3 running next. Okay, in this case task 3 would run for 0.3 ticks before task X runs. Okay, so now you see that everything is in reference to ticks and not real time. So this is a simple or slightly simpler explanation of how Lindsay actually implemented it in his code. In actual fact, there are more tasks that he added in order to achieve this. But I think you don't really need to know how exactly it works. All you need to know that it is now in reference to ticks, and then you just assume that when the schedule is called each time, it's the start of a new cycle, and everything else works pretty much the same way. You just call delays in terms of ticks, and yeah. It's probably also worthwhile just putting in the tick numbers there. So this will be tick 0, then 1, 2, 3. So the time between the ticks can now be variable, because, for example, if one of the interrupts has been missed, so what we can do is give an example of that. So let's say you're expecting there to be another interrupt somewhere here, which would be for the start of tick 4. Now, if, for example, this particular interrupt at tick 3 was missed, then, and it only occurred, let's say here, all that would change is that the task X would run for longer. And then tick 3 would start there. But nothing else has changed in terms of the tasks that have been run between between tick 2 and 3. It's just the time between tick 2 and 3. The real time between tick 2 and 3 has changed. Okay, so because of this asynchronous implementation, some parts of previous years Lab 3 are now not really relevant, so that's why we are not doing 3.1 to 3.4, I think it is, because those ones rely more on implementing this with real-time synchronization. So I'll try to explain Lindsay's code when I get to that section, but I'm still not 100% on that, so please don't complain if I get things wrong. Yeah, but that explains the difference. Using the asynchronous timer code that Lindsay has developed now means that the scheduler overhead is effectively 0. And this is because the time that it takes to execute the scheduling code does not detract from the time that the CPU has to work on the fixed computation of the periodic tasks during that particular tick. Because of this reason, we've removed the analysis of how the scheduler schedule overhead affects CPU utilization and the scheduler performance in this lab exercise. So I think overall your lab exercise has gotten a fair amount shorter than previous years. So in your skeleton code, what you will see is that there are a number of additional tasks and functions that Lindsay has implemented in order to implement the interrupt-free timer code. Your code that you will be including to do the scheduling should be put after the comment that says your RMS and EDF scheduling code should start here, and it should end before the start task code. The start task code is implemented for you, and you should not need to edit this code. The function lk_time_get is analogous to the getTime function from the previous year's task, and it will read the current time in number of ticks, and the lk_time_delay will delay or block a task for n number of ticks, and this is analogous to the OS time delay function. Okay, whenever you call an OS function, you should be checking for errors using the CE macro that you can define here. I think that's been covered in the last year's lecture as well. Okay, I might switch over to the actual code now and explain it from there, because I think most of this is explained pretty well in the document and also covered in the lecture, the second lecture from this week. This is the skeleton code. Now, while most of this code is the implementation of Lindsay's interrupt-free timer, and you don't really need to know exactly how it works, it probably would be at least useful to be aware of a few things, and I'll try to point that out now. So in addition to the 3 periodic tasks, or the number of periodic tasks that you will be running as part of Lab 3, there are 4 other tasks that make up this code. One of them is the start task, and the other 3 are part of Lindsay's code, and they are the task awaker task, task relay, and task timer. There are also obviously the other idle and statistics tasks that are part of the real-time kernel. Now, Lindsay's task awaker task will end up having the highest priority of all the user tasks. Then following this will be the start task and your active tasks. And then following the active tasks, or the periodic tasks, whatever you would like to call them, would be the task relay and the timer task. So they will have lower priority than the active tasks. So you might want to just quickly read through some of the comments in this interrupt-free timer code section, but don't worry too much if you aren't able to understand it that well. You should not need to change any of this code up here, but you can comment this line out if you don't want it to print at every tick. So the other things that you probably should be aware of is, as I mentioned before, this LK time get function and the LK time delay function and the LK wait function, which is here. So those are the ones that will be used in the code below. But like I said, you don't need to know exactly how it works. It would be useful to read Lindsay's comments though. Okay, so your code for this lab task will be implemented in this section here. I've already added in the schedule procs and init scheduler, two empty functions, just so that when you download this zip file, you can compile it and run something without errors. And the start task code is here. So there's a lot of stuff in this start task, but there's not that many different things that are occurring. So the first section is initializations. Initialization of Lindsay's code and creation of the tasks for Lindsay's code as well. And then there is a call to this initial init scheduler. So this function should have, well, you'll be implementing the code for that, and it should be initializing any data structures that you use as part of your code, initializing the initial priorities of the tasks, and also creating the periodic tasks. After that happens, there are a number of printf statements you can just look over for now. Then we go into a while one loop, and the first thing that occurs there is a call to this schedule procs function. So that is also something you'll implement, and within this schedule procs will be your code to implement the EDF and RMS scheduling algorithms. After that, then there will be a printout of the current tick and a call to LK time delay for one tick. The global variables gticks executing and gticks idle are just used here to keep track of how many ticks during which something was executing and how many ticks during which it was idle. And then eventually you just repeat that loop. So the main things happening in this start task loop is that you run schedule procs and then you sleep for one tick. Okay, so within schedule procs, you will be deciding which of the periodic tasks to run. So you may need to add more code here to implement the general function that will be used as the periodic task function, which I believe is covered in the lab sheet. Yeah, so there's a skeleton of the periodic task function here. Note that a difference from last year is that the LK wait function is used to replace the busy delay function. So this one's analogous to the busy delay. So what it does is it's simulating a fixed computation. In this case, it's going to take k number of ticks, which is fed in using this. Yeah. Okay, so the other things that I wanted to point out, I think I've covered most of what I wanted for this. Okay, so there are some things when you get to certain sections of the lab, you may need to modify within this OS config file. So if you read the comments here, you will say it will say what functions are accessible once you enable certain definitions on the left here. Okay, the other thing that I forgot to cover was when you first download this code and you run it, I just wanted to cover where it is that it actually does the code for these printouts. So what it will be printing out is tick, processor, num idle, and num busy at the very beginning, and then each tick it will print out the value for that, where tick is the tick, processor is which process, process is which process is currently being executed, otherwise it will show idle if there is no process being executed in that tick. Num idle is the accumulated count of how many ticks were idle, and num busy is the accumulated count of how many ticks were busy. So this code is actually contained mostly in the start task. So the headings are printed here, and that is only done once because it is not in the while one loop. Then it will print the tick here, and then when you actually call this LK time delay, it allows your other code or the periodic task to run, and then within the LK wait function, which should be called within your periodic tasks, that's where it will print out the task that's currently executing. Okay, so all of that printing is done for you, so you don't need to worry about that. And then after the LK time delay call, it will either print idle if there was no process being executed, or otherwise it won't. And then the final two values are printed here, which is the number of ticks idle and the number of ticks executing. Okay, now the other thing that you might want to print is when you've missed a particular deadline, just to notify that a deadline has been missed. I think that's part of your question sheet as well. Okay, so that should cover it for the brief overview, which wasn't so brief in the end. But any other issues that you have, you can address in your lab session.